We're going to look at verifying trig identities. So here are some common kind of simple identities that we're going to use to verify some more complicated identities. So again, these are good things to have written down on a separate piece of paper for you to refer to when you're working on your homework. So let's do a couple of examples. So first we want to verify the identity cotangent theta times cotangent theta plus tangent theta is equal to cosecant squared theta. So just like when we're simplifying identities, we want to rewrite these in terms of sines and cosines preferably, and then maybe tangents, because those simplify the easiest. And what you want to do is you want to look at the most complicated side and try to work with that side and get it to equal the other. So right now we're trying to verify that this is true. Now because we're verifying this, we cannot treat this like a true equal sign until we are finished. That means that you cannot multiply both sides by something, divide both sides by something, add or subtract both sides by something. You have to work with one side at a time. You can't cross over the equal sign. So since this side looks more complicated, let's work with that. So one thing I might do first is distribute this cotangent through the parentheses. So that would be cotangent squared theta plus cotangent theta tangent theta. And then before I start changing these things into sines and cosines, I am actually going to look over here at this cotangent tangent theta. So, and that is because cotangent is the reciprocal function of tangent. So cotangent is 1 over tangent. That's being multiplied by tangent theta. And then we'll notice that tangent theta over tangent theta cancels. So that'll just be 1. Okay, now from here we have cotangent squared theta plus 1. Now that should look a little familiar to you. So if we go back and look at our trig identities, cotangent squared plus 1, or 1 plus cotangent squared, is equal to cosecant squared. So we can go ahead and rewrite this as cosecant squared theta, and that's what we were trying to get it equal to, so we have just verified that this is a true identity, or that this identity is correct. Alright, let's do another one. Okay, we want to verify this identity. Sine theta times secant theta times cotangent theta is equal to 1. This left side is obviously the more complicated one, so let's work with that. And let's change these secants and cotangent into something with sines and cosines. So we'll have sine theta. Secant, remember, is the reciprocal of cosine, so that'll be 1 over cosine theta. And cotangent is the reciprocal of tangent, or it's also cosine over sine, and that might be more useful, so let's use that one. And that's using one of the quotient identities. Okay, and then from here it's pretty nice. We can notice that sine over sine cancels and cosine over cosine cancels. So that reduces to just 1, and that is what we wanted to verify that it equals. So we are done. Let's look at one more example. Alright, this is a little more complicated. Both sides look not very simple. So again, let's try to work with the more complicated side first. So let's see, what I might do is break this up into 2 fractions. So that would be 1 over sine cosine minus 2 cosine squared over sine cosine. Now the first fraction doesn't simplify, but the second fraction we can get rid of one of the cosines on top with the cosine on the bottom, where they simplify. So that'll be minus cosine theta over sine theta, which cosine over sine is cotangent. And then we've got this this? 1 over sine cosine over here. Now if we look at this didn't really simplify a whole lot. So this side might not be the one we want to work with. So let's go ahead and work with the right side instead and see if that'll get us anywhere. So tangent theta is sine over cosine. Cotangent is cosine over sine. Now let's try to get a common denominator, because if you look at the left side, this is all over one denominator. It's over sine and cosine, so that might be beneficial for us to do. So we're going to multiply the first fraction by sine over sine to give it the sign on the bottom that it's lacking. And let's multiply the second fraction by cosine over cosine to give it the denominator of that one what it's lacking. Okay, and let's go ahead and distribute or combine. So sine times sine will give us sine squared, and that's going to be over sine cosine. Cosine times cosine is going to be cosine squared over sine cosine. Okay, we can combine those over 1 sine cosine. So sine squared theta minus cosine squared theta over sine theta cosine theta. Okay, so if we look at what we're trying to get it to equal, we want it to be 1 minus 2 cosine squared thetas. So we've got a cosine squared theta here, so it might be beneficial to try to rewrite sine squared in terms of just cosines. And if we look up at our identities, we've got sine squared plus cosine squared equals 1. So what we can do is we can subtract that cosine over. So we get sine squared theta is equal to 1 minus cosine squared theta. So we can go ahead and use this expression to rewrite sine squared theta in terms of cosines in our example down here. So let's see, I'm going to write this over here. So sine squared we can rewrite as 1 minus cosine squared, and then we've got minus another cosine squared all over sine theta cosine theta. And then we notice that we have two like terms here. We've got cosine squared and cosine squared, so we can combine those into negative cosine squared, or negative 2 cosine squared. And that is still all over sine theta cosine theta. And that is exactly what we wanted to get it to equal. So we have just verified that this identity is true. So when you are working with these, you want, just like when we were simplifying trig functions, you want to rewrite these in terms of sines and cosines usually. You want to try to work with the more complicated side first. In this case, there were two complicated sides, so we tried both, and the one that ended up simplifying to match the other side was the right side in this case. Okay.